I want to figure out some stuff that happens to arcs in slow motion, and hopefully we can see it on camera.
So the Slo-Mo guys and ElectroBOOM did this really interesting video on high-speed footage of sparks in air. They did some stuff with alternating current, which honestly I'm not terribly interested in, and some stuff with direct current.
Oh!
It's working!
All right,
it's working.
I triggered it.
Which is all sorts of interesting.
Okay.
We are at 875,000, which is pretty much as high as we can go in color.
Fundamentally, they found it was very fast.
So here we go. Playing back. Oh, it's all the same.
It's all instantly the same.
That the actual spark itself happens in about a millionth of a second, and then sort of takes about 10 millionths of a second to fade. So how could they get better footage of this? Now there are simple solutions, like you just need a faster camera. Well, that's actually not really an option.
Yeah, so this camera will let us go up to, we've only ever done 1 million, but it will go up to 1.75 million frames a second.
This is pretty much top of the line and probably already costs well over $100,000. There is no sensible option for making these cameras faster. So that's the logical solution, right? The solution a rational man would come to. Well, it's often been lamented that a practical and rational man will adapt to the world, where a irrational man will try and make the world conform to him, which regrettably means that most of the change you see in the world is caused by irrational people. So is there a irrational solution here? You know, maybe making the lightning go slower. Maybe 20 times slower. Because I can tell you, they're not going to make their camera go 20 times faster. Well, that would be impossible, right? You would need godlike powers to slow down the lightning. Or maybe just stumble on it by random mistake in the lab somewhere. Welcome to Lady Luck. So let's start with something simple. So for this remarkable demonstration, you will need yourself a nothing special plastic cup. Just a regular polyethylene cup and some water. I've got mine in a syringe so you can see it better. So what we're going to do is we're going to get a nice little drop on the end of the syringe like that. Then you're going to charge up the cup with static electricity like that. And then just going to bring one up to the other. And boom! And does it again. Now that little twitch there is called a Taylor cone, named after the guy who worked out its shape. And I'll be fair, the guy was bloody smart. I mean, just to put this into maybe a wider context, without those Taylor cones, there might not even be life on Earth. Now, whenever you look skywards in summer, you might notice one of these things, which, believe it or not, are actually still pretty poorly understood phenomena, with the two principal questions being what causes the charging and what causes the rapid discharge. I mean, you might remember at high school they said that it was hard to build up static charges when things are wet, which is very true. So whence come thunderstorms? I mean, they're obviously quite real and relatively easy to film at 1,000 frames per second, which is the sort of thing you can get in a high-end smartphone these days. And when you film these things at about 1,000 frames per second, I'm going to guess these things are about 2 kilometers long, it takes about 30 or so frames. I'm going to guess to travel a kilometer or so. So that's a lot faster than the speed of sound. Now, one of the reasons why thunderstorms aren't very well understood comes by dint of the fact that thunderstorms are intrinsically difficult to study. They're very big, and when lightning happens, it happens very quickly and in a tiny portion of the thunderstorm. I mean, I can barely get a nice high-speed footage rig set up to record a single drop, let alone the idea of doing this inside a thunderstorm. But that all or nothing phenomena kind of bugged me. I mean, people have speculated about the disintegration of the droplets being important for this discharge. Hell, even Taylor mentioned this in his paper before I was even born. So these are now the words of a man long dead. The disintegration of drops in a strong electric field is believed to play an important part in the formation of thunderstorms, at least in those parts of them where no ice crystals are present. A bit about the ice crystals, by the way, is kind of throwing shade on the idea that you need ice crystals for thunderstorms. And me, I don't believe a word of it either. I think you just need a liquid with a dipole. Now, Taylor's high-speed photography was milliseconds. which can now be outclassed by some guys on YouTube by about a factor of 1,000. Hell, even my, by comparison, mediocre equipment is about 100 times better than what Taylor had. So I figured I'd take a look at some of those Taylor cones. I mean, all you need is a few thousand volts and a drop of water. So in the first case, we're going to just look at this exact phenomena, where it's a drop on the end of a syringe. So here we are. This is filmed at just a lick over 40,000 frames per second. And what you find is, boom, that's it. That was everything. We'll go back and see exactly how long it took in a second, but the rest is basically just the kinetic relaxation of the droplet. So if I blast through that again at sort of fast speed, then we're going to come back and we're going to take a look. Boom. There we go. And it's come back. And it really is. The whole thing is over in a single frame. That's it. That's it. It's all happened. 1/40,000th of a second. This cone has gone from being charged to basically having completely lost its charge, which is why it then just relaxes. And how that happens, that's actually a much more fiddly question than you might think. And just to show you how reproducible it all is, here it is again filmed, slightly different conditions, and what we again find is the drop stretches out and boom, it's all over in a frame. That's all it takes. And it's over. The whole thing after that is just the kinetic relaxation of the droplet. But I'm going to see if I can zoom right in on that. So here we are, all zoomed in, and boom, that's all it takes. Right, let's play that back a little slower. So it really is, it's just one frame, and that gets rid of all of the charge that was on this drop of water in the first place. And from this, you work out that when those cones form, they happen incredibly quickly. And they only collapse because they're ejecting charge somehow. And then I'm like, well, maybe I should just put these drops on a Wimshurst machine in and see what happens then. I mean, the Wimshurst machine will quite happily generate tens of thousands of volts. We crank on the handle. Oh, yeah, you get some pretty juicy sparks off these things. So roughly the electric breakdown of air is about 10,000 volts per centimetre. So what you're looking at there is about 50-odd thousand volts. And if we, I'm going to go, yeah, if you close down the gap, eventually you'll get usually more sparks, but less boomy sparks. In fact, then it's like, hang on, maybe I should put some drops of water through this very intense electric field. So here we are recording at about 20,000 frames per second. And you might get a suspicion. You see how all the drops sort of elongate as they come through this powerful electric field? That's kind of interesting. We've got a big drop coming down here. So what do you think is going to happen with the big drop? And he's stretching out. Nothing. And okay, well, maybe we'll get something with one of these guys. And oh, he's nicely elongated. And what about this one? No, nothing. Oh, boom! Look at that! Thunderfoot, torturer of water droplets. Let's go take a look at that again. So we're now going backwards. And boom! So you actually get to see the stretch out of the water droplet, and the actual spark itself is 1/20,000th of a second. It only really, there's a slight residue here, but this is all an artifact. This is a digital artifact of the camera. It only really lasts for one frame, and then you're just on the kinetic response of the droplet afterwards. And here we are doing it again, and what you'll find is if I actually sort of speed this up a bit, it's not hard to spot the droplet get zapped by the lightning. So nothing, even though you might not see the spark, yeah, it's like that boy, that one there. So let's go through and see his moment of glory, shall we? So you see the droplets all elongate in the electric field, which is kind of cute. And then, boom. Yeah, it kind of consumes it there. But again, it's only really one frame, 20,000 frames per second. So here we are again. I've this time moved the probes a little closer together. So now, yeah, I can see the real, some of them elongate better than others. But, yeah, there you go. So it's not hard to spot the one who gets zapped. And in this case, it's a relatively small discharge. Boom, that was it. You barely see it. That's interesting. It always gets that little sort of red glimmer there. That might be. But yeah, that's basically it. And after that, that, by the way, is a optical artifact. The sheet of paper. This is all immensely brightly lit because you're trying to film this thing at very high frame rates. So what you're looking at there is an optical artifact. There's a sheet of paper on the back there, white paper, that's got that's got a bit wet down the middle, and that's the image of the sheet of paper at the back. So if we play it backwards, you'll see, yeah, it's always there. It's just that, you know, when you actually get zapped by the lightning, boom, yeah, you get a bit more ripply. And here we go again, but I want you to watch these two drops here and the little ballet these two drops here perform. That they touch each other, and then all of a sudden, one little drop shoots off, one drop shoots off that side, and then, well, that's it. And meanwhile, boom, this guy gets zapped. But interestingly, the spark doesn't always hit a droplet. So in this case, I've got my probes quite a long way apart. But the interesting thing here is that the spark doesn't actually go through the drop at all. Let's see if we can find our spark. There we go. But when we do get our spark, you get an awesome reflection in the droplet here. So the origin of the discharge may well be that you're ejecting charged particles from your water droplet somehow, which happens very quickly. Now, if you think about it, the whole Taylor cone is just a sort of electrostatic repulsion getting equal to the surface tension. So, hang on. If it's just a matter of surface tension, then this is easy. I just need a liquid with a lower surface tension. Come on, think Thunder, think. What's a liquid with a nice low surface tension? Of nothing special, bubble liquid. And then, yeah, it's obvious. Bubble liquid. Okay, so you've slowed the frame rate down to about 10,000 frames per second, which you've got to do because I needed the resolution here. And there's always a compromise between frame rate and resolution. That's my drop of bubble liquid just there. And what you'll find is that it's got this little tail. And the tail just goes completely ballistic. And when you're doing this in real time, it makes this little sound, which sounds really weird. And it's really difficult to capture with audio stuff because it's quite quiet. Okay, so here I've improved the lighting a little. And here's our droplet. And as he comes down, oh, I've never seen that before. There's actually a little spark that comes up from this electrode here. So let's see. There's maxed out on that one. So there's a tiny little spark that goes up to the thread thing here. How many frames? 1, 2, 3. It's about 3 frames. So 3 10,000ths of a second. Anyway, okay. But, you know, when the spark hits it, not a lot actually happens. But then once it touches the electrode, it goes absolutely ballistic and just completely fills the air with these little threads. But even cooler, occasionally you get a spark there as well. So here are droplets going to come down. We're again filming about 10,000 frames per second. So this is half the half the frame rate of what we had previously, and boom, there's the spark. So let's go take a look at that spark. And what you find with the spark is it's much slower. So first of all, you see the spark hits this side and this side at exactly the same time. But remember, previously, the spark took place in one frame at 20,000 frames per second. Here, we've got 1 frame, 2 frames, 3 frames. So it's almost 10 times slower. And even weirder is it doesn't just follow the thread here, but it joins the thread here, but then arcs through to here for some reason. It's like, why? But interestingly also, I don't think these things here are artifacts. I think these are real.
We need to go faster, I
We
guess.
need to go way faster. Look at how bright that is. Is that all? What is this? Is this the electric fluff again? Look.
I don't know if it's
This
the
here.
flare from the lens or it might be the fluff actually.
It could be fluff.
I think these are real. Okay, let's try that one more time and see what we get. And it goes boom. But interestingly, it doesn't go completely ballistic when it gets hit by the lightning. The boom is interesting now because it's actually multiple frames. So here it's nothing, nothing, nothing. Oh, so we got leader coming off this side. We got a split. We got a forked leader coming off this side. And then 2 frames, 3 frames, 4 frames, 5 frames, 6 frames, 7 frames, 8 frames, 9 frames, 10 frames. And it then does this arc in much the same the way that it did it previously. So the reason this is interesting is that's 10 frames at 10,000 frames per second. So it's about 1,000th of a second, a millisecond. Whereas previously, these sparks took place in 1/20,000th of a second. That is, this spark is propagating at 1/20th of the speed of this one. But hey, maybe now is a good time to go back and take a closer look at those Taylor cones. Okay, so what we're going to do is going to put a single drop of water on this guy. Okay, let's try that. And there you go. Okay, so there you have the Taylor cone just going off again and again and again. You see the reflection of the Wimshurst machine in the... you see the reflection of me as well. It's cute. So we're now filming very small and very fast. So what you're looking at here is about the size of a drop of water. And we're filming at just under 200,000 frames per second. Give or take 1/5 of a million frames per second. And what you're going to see is our drop is extending. And I'm going to speed this up just a little until we get to the exciting. There is actually some twitching here. There is actually some activity here. But it's below the resolution what the camera can do. And boom, here we go. So you get a very fast spray, and almost instantly you've lost the charge on the droplet. So we're looking at that in reverse. And so you do get this sort of extension just beforehand, and then the acceleration. This obviously contains all the charged particles. This is probably linked to what causes the increase in the conductivity of the air, which gives you the lightning. And of course, we've got multiple shots of this. So this is another Taylor cone. This, by the way, is basically looking directly into one of the brightest torches that I've got. And boom, when it goes, these shoot off at like crazy speed, and instantly you lose almost all of the charge. So how did all the charge leave in those few little droplets? That's kind of the really interesting question here. And it's things like this. It's like, it's not quite obvious how that's actually meant to work. But, you can actually... These droplets, by the way, they're about the thickness of a human hair. So it's quite challenging to film this stuff. And just to give you a flavor of how weird these things can actually behave, I mean, what I'm going to show you here is actually sort of fairly common behavior. Yeah, first of all, the cones don't look, how should we say, traditional Taylor cone-like, you know, but the guy had vastly inferior data to this. But anyway, once you actually get up to the cones, they form a rod. That's fairly easy to understand, changes geometry. And then it breaks into droplets, and the droplets presumably all have either the same charge as this thing, which is why they're repelling, and they're actually moving away. But this guy is going to go back. So presumably these two have the same charge, and he's going to meet up, and then he tries to escape, and no, still not there. And now he's going to go back again, and this time he's going to leave for good. And it's like, yeah. So how's that work again? Now, I got to say at this point that the whole electronics thing ain't particularly a strong point of mine. And I had more than a small degree of apprehensiveness, surge protector or not, at plugging in $10,000 odd worth of high-speed camera in a thunderstorm.
Okay, stop. That was messing up the monitor.
Was it?
Yeah, that was that was like...
Likewise, static electricity is kind of known for frying sensitive electronics. And so for me, there was always this nightmare scenario that you get a nice big spark like that, followed by a camera not detected message on the computer. Thankfully, none of that ever happened. But I gotta say, a big thank you to all my very generous patrons who have supported this channel over the years. Because it's because of folks like you, I can now get footage like this. So would slowing down the lightning by a factor of 20 actually help the Slo-Mo guys? Probably not. You see, high-speed cameras aren't magic. You need enough photons to make an image on the sensor. Here, the thing you're trying to get an image of is the lightning, which isn't actually that bright. I can barely get an image of it at 10,000 frames per second. So even if the Slo-Mo guy's camera is 10 times more sensitive than mine, it'll maybe be able to go up to 100,000 frames per second on this. But beyond that, the lightning will probably be too dim to see in the image. Now, I should stress that a lot of what I've presented here isn't what you would call established knowledge. This is much more tipped on the research end of things, which, might be right, might be wrong. But I can tell you this is a fairly niche interpretation, and that if you take a look on Wikipedia on the Taylor cone page, you'll find there's no mention of lightning. And conversely, if you take a look on the lightning page, you'll find no mention of Taylor cones. Now, Taylor was clearly sniffing around this idea before I was even born, but lacked the equipment to do the actual experiments. But here, the combination of $100 or so Wimshurst machine and a fairly decent high-speed camera makes, I think you will agree, it's an interesting step towards a better understanding of lightning. So, what's next? Why, obvious. I'm going to go and throw a bucket of bubble liquid into an active thunderstorm. Maybe next year. And that's today's video. Hope you enjoyed it. If you did, maybe drop a thumbs up and consider subscribing. And as ever, if you really enjoy the work of this channel and want to support it directly, you can do it through Patreon. Thanks for watching.